Well, my research is mainly focused on modelling the mechanical behaviour of carbon epoxy composite fuselage joints using finite element modelling. So I focused really on countersunk joints for fuselage skin applications, so to model panel damage. And the idea behind it is that if we can model these joints more accurately, we can minimise conservatism in the joint design, and that leads to benefits in terms of reduced fuel consumption and reduced CO2 emissions into the future. I suppose our research mainly benefits aircraft manufacturers, and that's in two ways. The first being that they can dramatically reduce the cost of validating new aircraft designs. So at the moment that's heavily relies on physical testing, but if we can develop these accurate simulation tools, the aircraft manufacturers can focus more on numerical methods, and by that they can eliminate or reduce significantly their physical testing, and they can also bring their products, I suppose, to market more quickly, and that means as well they'll have a highly optimized product in the end, which obviously airlines would be interested in purchasing because they can reduce CO2 emissions and fuel consumption, which will have financial rewards for them as well. My work is funded by the Irish Research Council, as they're known now, and it's an Embark postgraduate scholarship which I got in 2009. I suppose my most accomplished achievement was the development of a 3D composite damage model for a commercial finite element software. And the idea is that this composite damage model can be plugged into the software, and it accurately predicts the microscale failure mechanisms that occur, and it predicts the effect that this has on ply behaviour. It was designed specifically for these composite bolted joints, but it can be applied to all kinds of applications, so it's quite a powerful tool. Well, I suppose the best research so far has resulted from experimental work that we did as part of this study, and that was actually a high-speed test series. So in those tests we tried to replicate the conditions of an aircraft crash situation. So we loaded the joints under tensile loading at high speeds, and we examined the crash worthiness of these structures. So crash worthiness is mainly concerned with energy absorption. So the idea is that if you can absorb more energy from these structures, you'll have a safer aircraft in an impact situation. And I suppose we found some surprising results in some ways, that if we made certain design modifications, like beefing up the laminate thickness, it could actually lead to some catastrophic effects where the energy absorption wasn't as good as you would have expected, and that our results from those studies actually showed that the fastener failure was key, as this induced catastrophic failure within the joint, and that level of crushing was very much controlled by that. The final task in the PhD was to create a graphical user interface. So this allowed engineers and industry to access the high-level tools that we've developed and implement them in the space of a few minutes, whereas model development times normally are several hours for these kind of high-tech models. So where that can go next is to be placed inside a kind of optimization framework where engineers can vary parameters of interest, develop very complex failure envelopes, and that will further optimize the design and drive efficiency in future aircraft structures.